Okay, so 192. This question was really complicated. First of all, they didn't give a diagram, so yeah, there was no way to actually understand what's happening. Secondly, they talk about deviation, but they don't specify deviation of what. They just say it. What does it mean over here? What context are they giving us? It could either mean the deviation of the velocity, or maybe the position vector, or maybe it could be the angle that it makes with the vertical. In this case, I think it's the angle that it makes with the vertical. And lastly, this question is just really tough to actually analyze, right? So yeah, it's one of those questions where if you don't know the method to solve it, you just cannot solve it. Yeah, so first of all, after getting stuck at this question, what I did was I went to the net and then I searched what the answer is. So Irodov 192. And then I got an answer, and over there, what they did was they took the angular momentum in the vertical direction to be constant, which is correct, right? So that's very much correct because the torque is completely in the XY plane, right? So talk about the suspension point, right? So that's completely in the XY plane. So that's very correct that in the vertical direction, your angular momentum, that component of the angular momentum, that's going to be constant. Right, but that's it. They didn't give us anything more than that. No, I mean, time dependencies, nothing, right? So, I mean, first of all, I thought maybe I can figure it out myself. Maybe I can figure out all of the properties as functions of time. But yeah, that didn't help because it will get too complicated very soon, and yeah, it's just not good. You cannot do that, right? So you can definitely make a computer do the thing for you and solve the differential equation. And as I solve, I really just mean um, I mean go to the next step from a particular step, right? So that's what we mean by solve. uh, right, but writing out equations, so functions of time, that is a hard thing to do. And I don't think it's I mean, I should even do it for just a single question, right? So that is not possible. I understand that. Then I thought maybe I can find some relation between the angles in the in the spherical coordinates, and well, that failed as well. So finally, I searched all kinds of questions that are similar to this, and then I finally got to the Wikipedia page of spherical pendulums, right? So I saw what they did there, and the method was pretty much similar to what the first answer that I got. What that did, yeah, pretty much the same method, but they did it for a general case, right? But I didn't like their notation and method, so yeah, I started from the scratch and I figured out what should we do when we get such questions. So the thing is, first of all, you don't really need the time at all, right? So you don't need any time dependencies. You just want the dependencies on the angle theta of different things, of course. So there are three equations that we can use. First is the fact that the angular momentum in the z direction, that's a constant. Uh, and using that equation, you can write v tangential times sine of theta. That should be a constant, and because it's a constant, it should also be equal to the this value, whatever it is, at the initial condition. So that will just be u tangential sine theta naught, right? Then you can also use energy, right? So work energy theorem, and from that you can write v squared is equal to u squared plus 2s. I know, torque is there and everything. It's not a constant acceleration, right? But the work done by torque, sorry, what I'm saying, tension is there and everything. It's not constant acceleration, but work done by tension is zero anyway. So that integral, I mean, that just goes to zero. And then you just have the other thing, which is our constant gravitational acceleration and stuff. And then doing that, you just get plus 2gr times cosine of theta minus cosine of theta naught, right? That's one other equation that you can get. And finally, you can use the fact that the velocity is perpendicular to our radius, right? So our radius vector, that's our position vector. And using that fact, you can say Vz is equal to Vr tan theta. So it's not saying anything about what V tangential is, right? Because that's not important. Yeah, v tangential could be anything. If this equation holds, then that's it. The thing is that your radius will not increase if this happens, right? And which must make sense. So if your radius does not increase, then your v dot r thing, that must be zero. So yes, I made a whole video on this thing, on how these three equations are um, derived and everything, right? And special cases and everything. So just go watch that video. Yeah, it's named Spherical Pendulum, right? And the first, I mean, the first line itself, it says spherical simple pendulum. And yeah, so now that we know these three equations, we're ready to solve this. Oh, and also you need to know the fact that they want the extremum value of theta, right? So for the extremum value, your v radial and your v in the z direction, both of these things must be zero. Yes, your v tangential must not be zero, but both of these must be zero, right? So if one of these is zero, then the other one must also be zero. That's pretty obvious, right? So if v radial is zero, vz will also be zero automatically. Yeah. So that's what our critical theta values. So the extreme values, right? Okay. So now we are ready to do it. So let's see what they gave us. A small ball is suspended from a point O by light thread of length L. Then the ball is drawn aside so that the thread deviates an angle theta. So initially they are saying it's theta angle. So okay, we'll have to use some other notation. I'm gonna use theta naught till the end and then just put theta in there once I'm done. From the vertical and set in motion in horizontal direction. So what they are saying is like the yeah, it's completely the tangential direction, right? Yeah. So, and when I say radial and tangential, I actually just mean radial in the xy plane and tangential in the xy plane, right? So that's why VZ even makes sense, because otherwise it wouldn't, right? So what they are saying is, right, initially your theta is given and your u tangential is your u, because all of the other things, so u radial and yeah, that thing is just zero. Okay. Huh. Okay, what is the initial velocity that has to be imparted to the ball? So what must u be such that it could deviate the maximum angle? So look at that, that's an extrema condition, right? So because of that, what will happen is that your v tangential will be the same thing as v, because vr and v z will be zero. So what is the initial velocity that has to be imparted to the ball so that it could deviate through the maximum angle pi upon 2 in the process of this motion? Yes. So when they say deviate, what that means is like the new angle, so the final angle will be either theta plus pi upon 2 or theta minus pi upon 2, right? Well, I mean, clearly theta should be less than pi upon 2, only then would it actually make sense. I mean, it can be bigger than pi upon 2, and yeah, that can happen. I don't like the feel of that. So we'll just say theta plus pi upon 2 or something. Well, anyway. So if this is like theta plus pi upon 2, then sine of theta will become, but yeah, okay, theta plus pi upon 2 is also an obtuse angle. So in any case, you're going to have at least one obtuse angle, right? They should have given us if it's accurate or not. Okay. Fine. So we'll just figure out what this critical angle is and like some equation with it, and then we'll see what happens. So in this particular case, this equation is just redundant because 0 equal to 0. And then u tangential is the same thing as u, and v tangential is the same thing as v in this case. So v sine theta is equal to v sine theta naught, and then v square is equal to, yeah, all that stuff. So from that we can say, okay, v is just going to be u sine theta naught upon sine theta. So this just becomes u squared times sine squared theta naught upon sine squared theta minus 1 is equal to 2gr times cosine theta naught minus cosine theta, sorry, cosine theta minus cosine theta naught. Yes. Now this thing can be written as u squared upon sine squared theta, and then you got sine squared theta naught minus sine squared theta, which is the same thing as cosine squared theta minus cosine squared theta naught. So you can factor that, right? A squared minus b squared, you can factor that out, and then this just becomes I mean like sine of theta plus, sorry, this is not what it should be, cosine of theta plus cosine of theta naught, right? That's just equal to 2gr. There we go. So this goes over here, sine squared of theta naught. Now, what they are saying is that, where it go? Now it's deviating by pi upon 2, right? So sine square theta naught. Um, oh, wait, okay. No, they are saying, okay, like, okay, theta is going to change. So, yeah, I get it. Cosine theta, instead of that, you should just have cosine of theta plus pi upon 2. No, that's just not correct. What about theta minus pi upon 2? Well, yeah, that would be correct. Only then it would make any sense. If it's going to be theta plus pi upon 2, it's like cosine of theta naught minus sine. It can happen. Okay, it can happen. Fine. Fine. So it's just like, yeah, they should have told us whether or not. So yeah, like what kind of condition is this? Hey, wait a second. Okay, they are saying maximum angle of pi upon 2. So which of them is bigger? Is V bigger or U bigger? So maximum angle of pi upon 2, huh? Deviation though. It could either deviate to get bigger or smaller. Both would be considered as deviation. So then how does it make sense? Ah. Oh, hey, wait a second. When it does this, oh yeah. So what I'm thinking is, it's drawn and then it's imparted some velocity tangentially. So that's one extremum. Okay. So is this, so the initial condition, is this a maxima or it's a minima? We don't know. We don't know for sure. Oof. Yeah, this suddenly becomes so complicated. Oh, you got this equation. We can use this thing to like figure out something. So cosine theta minus cosine theta naught. If your theta is let's say theta plus theta naught plus pi upon 2, and this would just become minus sine theta naught minus cosine theta naught. And for this to actually even make sense, what should happen is the theta naught should be an acute angle. So this would really just be v squared is less than u squared, which means that v is above u, right? If v is above u, sorry, I mean the condition for v. So for one, I don't want this. Yeah, so when I said v squared is less than u squared and v is above, what I mean is the position where v squared, where v happens, that position is like above whatever the position of u is, right? So in that case, hey, okay, that's just giving us the same thing. That doesn't make any sense. It could be anything, you know, right? It could be both of those conditions. So now what do we do? Just do it. Like just put negative sine theta right there, or sine theta, doesn't matter. You wanna put plus minus right there, you know? So u squared cosine of theta naught plus minus, I know, sine theta naught is equal to 2gr sine squared theta naught. They didn't tell what kind of condition is this. Is the maxima or minima or whatever. Fine. But this is how it is, huh? Yeah. Okay. So that means for this to actually go, I mean like deviate by pi upon 2, what should happen is that u should just be square root of, I'm gonna take that out anyway. So sorry, sine theta naught, which is positive by the way, because theta naught is an angle less than pi upon 2, sorry, less than pi, right? So 0 to pi, positive sign. And then you got square root of 2gr and this upon square root of cosine theta naught plus minus sine theta. And then in the end, theta naught, instead of using that, we'll just use theta. So there we go, you got our answer. This should be the velocity. So our answer will be sine theta square root of 2gr upon square root of cosine theta plus or minus of sine theta. This plus or minus is because we don't know whether it deviates to get bigger or smaller, right? Next, 193. Right. Okay, a small body of mass m tied to a non-stretched string moves over a smooth horizontal plane. Okay. The other side of the thread is being drawn. So figure 1.49. Where is it? Oh, this is 1.49. Fine. The other end of the thread is so non-stretchable thread. Okay, makes what? Sorry, moves over a smooth horizontal plane. Understandable. The other end of the thread is being drawn into a hole O. Oh, like this. Okay, okay, okay. Understandable. Right. With constant velocity. Right. Find the thread tension as a function of the distance r between the body and the hole. What? Find the oh, so this body goes like this, and then so yeah, it was just rotating like that, but then now you're pulling it. Okay. Find the thread tension as a function of the distance r. Yeah, between the body and the hole. If at r equal to r naught, the angular velocity of the thread is equal to omega naught. Understandable. So what we do, first of all, just consider this whole system of the thread plus mass thing. So you got this force over here. You will just consider O to be your origin. So the torque due to this force, that will be zero because it's along the radial direction, right? So yeah, r cross f will be zero. That just means the angular momentum of this whole system remains constant. Well, the string is just massless. So yeah, this guy has the same angular momentum. And then you might be thinking, well, I mean, it clearly is changing. So what's keeping omega constant? The thing is, omega is also changing as r changes. So yeah, I mean, what equation do we have? We just have r, so like mr squared is the inertia. So just have r squared omega is equal to whatever its initial condition was, like r naught squared omega naught squared. There we go. So what do you want though? The tension, of course. So the tension will be just the wait. There's going to be this angular acceleration as well. Where does that come from? Uh, Wait. Yeah, I mean, there must be an angular acceleration because, okay, angular acceleration is there, cool. And then what? Um, that times r will give us the actual tangential acceleration, which is what the force will be. Okay, 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 understandable. But really, does have centripetal acceleration is there. Okay, what about the tangential acceleration? Does that thing change? I guess it doesn't change. No, it should because mr cross v vector is our angular momentum, and then here your r is decreasing, so v must be increasing. But that just means that yeah, your tangential acceleration is there. But who is making it accelerate tangentially? Uh, Wait, what? Oh, yeah, who is making that happen? So wait, what is the total acceleration vector though for this guy? Right, you just have r double dot, which is like not no, I mean it's not non-zero in this particular case. Okay, r double dot. Oh, there must be that. Okay, okay, understandable. And then we got minus omega squared r, this in the radial direction, plus t hat times, right, it's going to be what? 2 omega r dot. Okay, where was I? Sorry, 2 omega r dot plus r alpha, right? Yeah, so even though there is alpha, this guy cancels that up because r dot is like negative and everything. Yes, that cancels up, and in fact from here you can get this equation. So yeah, that is the angular momentum equation. And then this other equation is also there, which I don't know. What is this? Yeah, your r dot double dot is definitely decreasing. Okay, so this just tells us, okay, tension is equal to mass times this acceleration, which is like radial direction. So yes, it's going to be omega squared r minus r double dot. Yes, so you just got negative t r hat. That's our force. That upon m, that should be acceleration. This component is just gone. So you just got r double dot minus omega squared r times r hat, right? So this is the equation we are looking for. Now, how do I get r double dot? Yeah, that's confusing. So you got r as a function of omega. Okay, cool. But now what? Uh, Wait, the force is constant or something? So it's 193. Did any other condition that you give? Oh, a constant velocity. Look at that, huh? Okay. So r double dot is just zero in that case. So constant velocity, perfect. This is zero. Right, now you got it. So it's gonna be m r omega square, and then yeah, from here you can figure that out. All right. So you want this as what? As a function of distance r, of course. So you want omega in terms of r, which I mean is not a big deal. It's like this. Why is this squared over there? And then upon r squared, and then you will put that in here. So tension will just be m this guy squared. So r naught power 4 omega naught squared, and then you got r power 4 and yeah r cubed. Yes. So that's our tension. Nice. So 93 done. 193. Yes. Okay. 194. A light non-stretchable thread is wound on a massive fixed pulley of radius r. 194. A light non-stretchable thread is wound on a massive fixed pulley of radius r. A small body of mass m is tied to the free end of the thread. So we've got this pulley. We got yes, tied to the free end. So it's vertical, right? The whole system is vertical or not? Didn't give us anything, huh? Oh, come on, please. How ambiguous can your questions get? A light non-stretchable thread is found on a massive fixed pulley of radius r. So, okay, small body mass m tied to free end of the thread, free end of it, whatever. At moment equal to 0, the system is released and starts moving. It's under gravity, of course, and the only possible conclusion is that it's in a vertical plane, because otherwise, why would it move? Yeah, but come on, really? Why did you do that? Why did you not just say it's vertical plane? Find its angular momentum relative to the pulley axle as a function of time. It's what is 8 over? Oh, the small body, I think. Okay, fine. That's too weird. It's wound. Sorry, so it's not. Yeah, it's like this. Okay. Find angular momentum related to the pulley as a function of time. No big deal. You can do it. Oh, you want angular momentum? Oh, huh. Wait, that's like so easy to do, you know? I mean, think about it. It's just gravity acting over here. You just want like what r cross f, mg is forces acting like that. You got r vector is like this. So in the end, you're just doing this vector cross this vector. So that's like, yeah, mgr is your torque. So that's a constant thing. Understand that it's a constant. So this times time. There we go. That's our angular momentum of the whole system, as seen from this point. That's what we want, right? Related to pulley axle. What? Come on. What was this? Did I miss something? It's massive and everything, yes. But yeah, like mg on this pulley is acting like that. That's like this tension forces. Those are internal. They don't do anything. And yeah, this also doesn't do anything because it's right at the axis point, and that just means no torque. Yeah, I mean, if this guy's center of mass was off the center, then this would make sense. But right now, yeah, this is just like that. It's just not there. Okay, understandable. Right, so then that's it. Our angular momentum is just mgrt magnitude wise. 195. A uniform sphere of mass m and radius r starts rolling without slipping down an incline. Is there friction? No, there's no friction. Okay, then 194 must be correct. What I did. Yes. 95. A uniform sphere of mass and radius r starts rolling without slipping down an inclined plane at angle alpha to the horizontal. So it's a uniform sphere. Hmm. Finally, time dependence of the angular momentum of the sphere related to the point of contact at the initial moment. So this point, huh? How will the obtained result change in case of perfectly smooth inclined plane? Oh, so this case is just like a rough inclined or whatever. Um, Wait, what? I mean, okay, the friction force does not create any angular momentum in the first place. Yeah, because it's just directed along this line, so it can't do anything. You got mg sine theta like that. You also got mg cosine theta, which might play a role. No, it doesn't. Normal force normal force just cancels that. So if this guy comes over here, you got mg sine theta in this direction, normal in this direction. Look, both of them will put the same torque, but in opposite directions. So that will cancel each other. So it really just like mg sine theta times r. That's our torque. So that times time. That's our angular momentum. This was why. Why did you ask me this? And does it change in case of wait, where did it go? Oh yeah, and what else was the thing? Where did it go? How will the obtained result change in case of perfectly smooth inclined plane? It won't change. It won't change. Friction. I mean, okay, now friction is just not here. So no difference, right? It's still the same thing. Wait a second. And moreover, this is not for just any I mean a sphere. It's for any body that has I mean it's like rolling with some kind of radius, right? For any such body, this will work. Wait. And what is the angular momentum? It is just the angular momentum of the center of mass, which is I omega, plus the angular momentum of center of mass, right? So angular momentum as seen the center of mass and angular of the center of mass, which would just be this guy's velocity, like this v. And oh, I'm getting some ideas from it. So mvr. Wait, yeah, right. For any time, any moment of time, you can always do this thing. So r, yeah, r cross v, and then that's m everything. It's gonna work. Yeah, it's gonna work, of course. Damn it. So our torque, which is just mg r sine theta, that's just sine alpha, whatever. That's equal to, wow, this is some weird thing happening. Okay, the derivative of this thing, uh, yeah, it's gonna be I alpha plus mr times acceleration. In case of pure rolling, what will happen is like alpha is equal to ar. Sorry, what am I doing? Um, Alpha is equal to a upon r and everything. So you can just figure out what the acceleration is right from this equation. And it's not that hard to do by itself as well. I mean, just gonna do like mgr sine theta upon the inertia of the asymmetric contact point and everything. Yeah, no big deal. I mean, this equation is not so different than what we usually do. I thought it would give us something really nice, but nah, just gives us a normal result. So there we go, mgr sine alpha, it's our torque. So that times time is our, yeah, whatever. Still, it's weird, isn't it? Because this actually should be working for all kinds of motion, not just rolling motion. So then, yeah, that's one equation we can always use. Okay, but then we don't have another equation. We will need more equations for that because alpha and acceleration both are now unknowns, right? Yeah, but alpha can be dealt with. Um, it's not pure rolling. Okay, unfortunately, it's not pure rolling. You cannot just do that. Fine, whatever. So this is it. This is the equation that we got. That mgr sine alpha that times time is our angular momentum at any time t. So that's 195. So yeah, in both cases. Right. 196. A certain system of particles what possesses a total momentum p and an angular momentum m relative to the point O. Okay. Oh yeah. Find its angular momentum m dash related to point O dash, whose position with respect to point O is determined by the radius vector r naught. Okay. Find out when the angular momentum of the system of particles does not depend on the choice of the point O. Okay. Uh, right. Radius vector is given by r naught. So you wanna right. So you wanna shift to some point like that, huh? Okay. Yeah, it will be independent when that I mean the middle term that you always get that cancels out for like center of mass and stuff like that, right? But if it doesn't, yes. So find out when the angular term of system does not depend on the choice of the point O. Okay, this kind of weird, right? Ah, it does depend most of the time. So what are these people talking about? I don't know. Just deal with it. Angular momentum as seen by point O dash. Sorry, point O is m, right? So your summation of mi ri cross vi is equal to m. Yes. And then you just want the angular momentum as seen by point O dash. So for O dash, you just have summation of mi ri dash vector, which is, I mean, it really is just, yeah, it's going to be like ri vector minus r naught vector, right? Something like that. I've done this so many times though. So you can do that over there, and then that will just become. But the thing is, if these points are stationary, wait, are these stationary? I think they must be, right? Uh, whose position is always from the vector, right? I mean, they must be. Otherwise, it will. Uh, what if these are not stationary? Then it becomes really complicated. But if these are stationary, then yeah. Wait, why did you say it in such a lengthy language? Determined by the radius vector. Is this changing? Is R not changing? I don't think it should change, right? Because if it changes, then the angular momentum as seen by that will be dependent on your, I mean, dr upon dt thing. Okay, be honest and do the most general thing. We'll see what we get. The summation of this can be done as summation of mi and then ri dash vector plus r naught vector cross um, vi dash vector plus v naught vector. I know. Uh, if it's stationary, then you just, yeah, you don't need this anymore. Vi dash is pretty much the same thing as vi. Right, and that's equal to our m vector. Now this can be broken down as summation of mi this thing, so cross vi dash vector and then plus this and that. It's going to be uh yeah, ri dash vector and then that cross v naught vector plus r naught vector cross vi dash vector, right, and then plus r naught vector cross v naught vector, right? This is equal to our angular momentum. Now this thing, so mi r dash vector vi, yeah, that summation is what we call m dash. So this is the angular momentum as seen by O dash, right? Right, and then you got plus the summation of this thing. So yeah, I will just say all of this, but it's gonna be like mi times all of that, and then yeah, it looks like a vector. It's not. It's just like addition. Okay, yes, and then summation of this thing. This is equal to angular momentum. So what should happen is that this somehow should become zero, such that these both of these would become equal, right? Because we want this to not depend. Yeah. Hmm. Well, think about it. Um, do we really need to break this as VR dash and then? No, we don't actually. I mean, think about it. Just think of this whole thing as R naught vector cross. Wait, did I just mess up somewhere? Yeah, no, it's correct. So maybe R naught vector cross our just V vector, you know? Yes. So the summation of mi R naught vector cross V vector, what's that? Yeah, that's just R naught vector cross P vector, right? So this other summation can also be taken out. So you can just have R, yeah, this thing. So something like summate, what was I doing? Sorry. Um, R naught vector cross momentum vector, right? As seen in O's frame, of course. Then you got this other stuff. So yeah, it's just going to be like summation of mi r. Wait, what? Ri dash vector cross v vector. Wait, what? Ah, that's very weird. Yeah, that is very weird. You know. We usually don't get such things, but now we are getting. Oh, it doesn't make any sense. Why don't you just break that in that and then this somehow, right? It really is just like v naught. So it's a summation of, sorry, summation of m vector, so mi vector, and then ri vector, and all of that cross v naught vector, right? Because v naught is a constant, and that's why you make it out. And now, what is this? Sorry, ri dash. Or would I forget that? Ri dash. So this thing is going to be like the mass times the position of the center of mass as seen in the O dash frame, right? Yeah. So if somehow that position is along V naught vector, we are done. In that case, we'll be done, right? Exactly. Yeah, that's like making sense though. Now that's making sense. Yes. Yes. And wait, what do you want? Find out when the, so it will actually depend on R naught vector, even if this somehow becomes a nice quantity. Unless of course a P vector is also along R naught vector. That is, so what should happen is that your R naught vector must be along P naught vector, and your RCUM vector, sorry, RCUM dash vector, that should be along V naught vector, or in other words, V vector should be along RCUM vector. So write it down. Okay, first of all, just write down this equation, you know. So it's gonna be like RCUM dash vector, and that times what was this once again? R naught vector, right? So that cross R naught vector, of course. Yeah, oh, sorry, M times that, of course. Wait, why doesn't it make any sense? Because like, oh, it should be V naught vector. That's why it's not making sense. M, and then you got V naught over there. Yes. So mass M and all that stuff happening. Understandable. Find out when the angular momentum of system of particle does not depend on. First of all, let's write down this formula, you know, because it's a nice formula, I think. So you can just write um, wait, what? We'll just use m naught for this thing. No, that's just, yeah, I mean, this equation is like good enough, I think. So m dash vector is equal to m vector minus, so minus r naught cross p, yeah, whatever, r naught vector cross p vector, and then why just put p vector right there? You can also put p vector plus the m v naught vector, right? So this is as seen in the, oh, what was I doing? Can't remember anymore. Yeah, this was as seen in the original frame O and m v naught vector. So what does this do? V naught is just that. So huh, I don't see how this becomes anything nice. Yeah, it's just really weird. Oh, sorry, what? It's not r naught. What am I doing? So you got p vector. That's why this was looking weird. And minus m v naught vector, and then you got r cum vector. R dash. Yeah. Yep. This is the answer. So that's nice. And now for the second part, when is this independent of r naught vector? So for any r naught vector, oh sorry, the choice of O. Wait, what? Does not depend on the choice of O. Wait. If it was choice of O dash, that would make perfect sense. But what do you mean by choice of O? Oh, so okay, yeah, like even going from O to O dash, that does not actually change the angular momentum. That's what you're saying. Understandable. So if it does not depend on that, then what must happen? Uh, then these must be equal. Then what should happen is r naught vector cross p vector should be equal to, sorry, is equal to, yeah, negative. So like r naught vector cross p vector plus, it's like equal over there, plus m v naught vector, and then yeah, this should actually be 0 for all values of r naught vector and v naught vector, whatever, right? So this should always be 0. Then yeah, well, and then r dash cum. Oh, it should be crossed, by the way. Yeah, it should be like r cross v. So both of these terms should be 0, because I mean you can just not change v naught and change r naught, right? That you can do. So yeah, like v naught and r naught are independent. We can choose anything we want for these values. So for any values in the world you want this to be 0, there's only one such way that this can happen. P must be 0, and either m must be 0, or like, I mean, okay, r vector cum, that cannot be 0 all of the time. So your m must be 0. So the only way this can happen is that the body does not exist. What? Wait, what? That's not making sense, is it? Okay, you can have a special case where a v naught somehow becomes 0. In that special case, what should happen is your p vector must be 0, so that this happens. Oh, it's complicated, huh? Yeah, well, p vector is oh yeah, I mean, like, yeah, if somehow your somehow your points are like, okay, the reference points are stationary, then what happens is that p vector will not depend on the reference frame anymore, because the reference frames are just all with the same velocity, right? And that would mean, yes, this will happen. Okay, that's nice. So all that should happen is that p vector should be 0, and then that's it, done. It won't depend on it anymore. Okay, just write it down. if v naught vector is equal to 0, then for m vector is equal to m dash vector for all r naught vector, p vector must be 0. Okay, so 196 done. So 197 now. Demonstrate the angular momentum m of the system of particles related to the point O of the reference frame K can be rewritten as m is equal to, okay, is the proper angular momentum in the reference frame moving transition at fixed. Come on, man. I mean, I have done this so many times. Why do you want me to do this once again? Center of inertia related to point O. Yeah, P is the momentum. Come on. I mean, why? Why do you want me to do this once again? I've done this 100 times before, right? It's the angular momentum of the center of mass. So this thing RCP, that thing is the angular momentum of center of mass plus the angular momentum as C by center of mass. So that's our proper angular momentum, right? And then yeah, that's not what it is. So why do you want me to do it once again? Anyway, just do it. Summation of mi uh, mi vector cross b vector. You know what? Okay, since we already have this formula, why not just use that? So what we could do is just say that your original frame that was of the center of mass, so the proper frame. So then m vector would just become this m whatever this thing is. So yeah, then this thing just becomes this, and your m dash vector is now rewritten as m vector. Okay. Yeah, I mean notation is different over here. That's why this becomes that. But in the end, the whole concept is the same thing, right? And then you got minus r naught vector plus p vector. So p vector as seen by center of mass, guess what? That's 0. That's 0, right? Yep. So that's 0. I mean, this whole term is going to be 0. So yeah, that's perfect. Yes, because like summation of mi vi vector is 0 as seen by center of mass. So no problem. And then this thing, mr dash com. So r dash com is now just rc as seen over here. And why is this in brackets or whatever? RC is the trace vector of the center of inertia related to the point O. It should really be RC cross P. It's a radius vector, you said. Then why are you taking a cross product? What is this bracket notation? I don't know what this thing is. Anyway, so yeah, it's just gonna be like plus. So this thing just becomes RC because yeah, now in the new frame, the position of RCOM is RC. So it's yeah, it's like minus and everything. Yeah, and then wait, it should not be this. Something's not correct about this. Wait, why is this in negative? It should be something's not correct. Wait. B vector. Yeah, something's not right. Did I derive that correctly though? It must have been, right? Yeah, all the cross products were in the correct order, so right, I never actually did something wrong. It can't be, of course. Then why is this thing the opposite of what it's supposed to be? It's minus m r dash com r dash com. Right, just like the radius vector of the center of mass in this new frame. Yeah, yeah, right. Something definitely went wrong in this derivation because this somehow doesn't make any sense. We got v naught vector. V naught vector is just the. Oh, sorry. Okay, it does make sense. V naught vector. What is V naught vector, huh? It's the velocity of the reference point as seen from the center of mass, right? It's not the velocity of the center of mass, right? So it's actually going to be negative vc, and that's why this negative becomes positive, and then you just get plus mrc vector and then cross vc vector. Yes, but what's mvc vector? That is p vector, as seen in the center of mass, of course, center of mass frame. So there we go. This is the thing. So yeah, I mean, I have done this so many times, right? Just this morning, somebody asked me to tell them what this, like, how is this used and whatever. Anyway, so yeah, this is a very useful thing, right? Let's go to 198 now. A ball of mass m moving with velocity v naught experiences a head-on elastic collision with one of the spheres of a stationary rigid dumbbell as shown in the figure 1.5. Wait, where's 1.5? Where's 1.5? I think it should be, yeah, okay. Stationary dumbbell, point mass, okay, ball, whatever. Yeah, collision with that. Okay, experiences a head-on elastic collision with one of the spheres of a stationary rigid dumbbell. The mass of each sphere equals m.2 distance L, whatever. Disregarding the size of the spheres, find the proper angular momentum m vector of the dumbbell after the collision, i.e. the angular momentum in the reference frame moving. Okay, yeah, I understand all that stuff. Right. I mean, what's this? It's gonna be like momentum imparted on this guy, well, that, so r cross momentum, right? That will be our angular momentum, of course. Yeah, yes, of course. So it stops, right? Actually head on elastic collision. Okay, that's kind of important. It's an elastic collision. Oh, come on, if it was fixed then we would have done this easily. It's not fixed. uh, right, wait, have I not done this before? I don't remember it. Yeah, I must have done this before, but I don't remember when I did. And I also don't remember any formula for it. Okay, an elastic collision with one of the spheres of a stationary. No, I must have done it, right? And I must have done a general case as well, where your x is variable. But now somehow I do not remember it. That doesn't look good. Let's look if I have done this before. Okay, whatever. We can just spend time doing that. Let's deal with it now. 198. Next page now. A ball of mass m moving with velocity v naught experiences a head-on elastic collision with one of the spheres of this. Whatever. Yeah. So what you want is just the total, I mean, a proper angular momentum, which of course is going to be the momentum that it receives, and then that times r, of course. So yeah, that's right. That's right. And what do we do? If this receives a momentum p, then what is the total energy of the system in the ground frame, of course, after the collision? Well, this guy was initially moving with v naught, so now it will be moving with v naught minus p upon m, of course. Yes. Okay, go and think about it. Yeah, it's gonna be v naught minus p upon m. Fine, it's like half small m v naught minus p upon small m, this thing squared. The change in the kinetic energy, that should be 0, right? So minus half m v naught squared. Okay, and then now initially the rod was at 0, dumbbell, whatever that thing is, and now it's at half I omega squared, and omega is just or you can write this as like, I don't know, half L squared. So that's the angular momentum, which is just R times P. So this thing squared, and that upon, yeah, and that thing upon, what do we call it? Our inertia, right? That has to be equal to zero. So this whole thing has to be zero, of course. So this just gives us half M, and then you got this V naught square gets cancelled. So it's just going to be like minus 2p V naught upon M plus P squared upon M squared. And then you got this guy, so half R squared P squared upon I squared is equal to zero. Some stuff cancels, I mean like that P cancels, this M stuff cancels, half cancels first of all. This just becomes minus 2v naught because M cancels, right? Remember? And then plus just P upon M, I guess, because M cancels and then 1P cancels, right? And then plus R squared P upon I squared is equal to 0. So now from this we can figure out what P should be. So P times 1 upon M plus R squared upon I squared is equal to 2v naught, right? And then of course we want the angular momentum as in the center of mass, so it should just be M upon R. That no, don't do that. Wait, what happened? Oh no, this went out. Okay, just wait a second. Please. Come on. Yeah, finally. Yeah, that's good. Right. Wait, did we not use capital M? Yeah, I mean, we just use inertia. So, it should also be this plus the energy, I mean, the translation energy is going to be like half P squared upon capital M, right? And that has to be 0. So that term should also be there. So yeah, you got all of this stuff, and then you got plus P upon capital M as well. Just gonna put that in here. Yes, this is nice. Looks good. Yep. Okay, so now that we have this thing, we can find out what P is, and then of course P is just going to be the angular momentum, which I'll say is L. They're using M or whatever. I'm going to use L, and L upon R. That's the thing. So yeah, this will do it. This must do it, right? Of course, right. Dimensionally, it should be correct. I mean, this is just momentum, and then you got masses of different kinds. That's like I squared, though. Yeah, why is that I squared? It's not supposed to be I squared. It's just supposed to be I. Now it's correct. Mr squared, and that's why just 1 upon M. Yes. Now, this thing is a double dumbbell, whatever this thing is. It's got inertia of these two dumbbells, so M upon 2, M upon 2. It's going to be Mr squared inertia, and then you also got the rod by itself. So is it dumbbell? Okay, it's understandable. So it's got L upon radius is it's going to be L upon 2, right? And 1 upon the mass of this dumbbell stuff. So right, head-on elastic collision of these spheres of a stationary rigid dumbbell. Mass of each sphere is M upon 2. So the total mass is going to be M. 1 upon M, and then you got R squared upon inertia. Inertia is just mr squared once again. So half mr squared plus half mr squared. So mr squared. And that's why it's going to be 1 upon M once again. That's equal to 2v naught. Right. So that just becomes 2L upon L. And that times 3 upon M is equal to 2v naught. So cancels. You just get L is equal to mv naught upon, so mv naught times L upon 3. So right, there we go. 198. Nice. But I do remember I did make some kind of derivation for this thing. I don't know. Wait, it's not 193, it's 198. Okay, 199. Last question. Two small identical disks, each of mass m, lie on a smooth horizontal plane. The disks are interconnected by light, non-deformed springs. Okay, spring of length L naught and stiffness X, stiffness K, or mu, whatever. Um, at a certain moment, one of the disks is set in motion in a horizontal direction perpendicular to the spring with velocity v. To the spring with velocity v naught. Okay. Perpendicular to spring. Okay. So you got these two disks. These are connected by a spring. One of the disks is put to motion now with velocity v naught somehow suddenly. Find the maximum elongation of the spring in the process of motion if it is known to be considerably less than unity. Okay. Spring motion is known to be considerably less than unity. Uh, yeah. You know what I'm thinking? I could just analyze this whole thing by yeah, doing that. Yeah, maybe that's not the good thing to do. Oof. What I was thinking is that this guy is accelerating because of the force over here. So I could just add a pseudo acceleration. And then once that's done, I just have this thing as seen by this guy. So I will have a better handle at this distance from the yeah, between these two disks, right? But hey, okay, we can do this without that as well, I think. Okay, first of all, what we want is the maximum elongation of the spring in the process of motion, right? So for maximum or minimum, your dr upon dt is zero. That just means your radial velocity, so radial relative velocity is zero, which just means like both of these are just moving in the same velocity in the radial direction. These might be moving in different velocity in the tangential direction, whatever. Moving in the same direction in the radial direction. Sorry, same velocity in the radial direction. Oh, and also by the way, the spring force, it cannot change the center of mass's motion really because it's internal force. So this center of mass is going to go with, yeah, we could do that, you know. So wait, the center of mass is an inertial frame. That's it. That's all you need. Yeah, that's all you need, really. You just need an inertial frame, and now just look at it with respect to center of mass. That's it. So this guy is now moving with v naught upon v naught upon two, right? It's fixed. This guy will always move with v naught upon two, and your omega is, or I should just say your angular momentum. Your because yeah, omega changes, angular momentum doesn't. So your angular momentum is just m, so about center of mass, right? That remains constant. That's the thing, of course. So because inertial frame and everything, so yeah, it's going to be, this guy's mass is m, this distance is going to be like l naught upon 2, and then v naught. Yeah, that's our angular momentum. So after some time, what happens is both of these have the same relative velocity in the radial direction. Yes, and I mean, we know it's just at the center of this thing. So whatever radial velocity you have, like this, as seen as center of mass, and this must have the same but in opposite direction. Yeah, understandable. So if they have the same radial velocity in the ground frame, then according to center of mass, well, there's no radial velocity in fact. Yes, yes, and that just means your dr upon dt thing is zero for this disk. Okay, and what does that mean? Um, no radial velocity. Okay, so that's just tangential velocity, of course. Wait, isn't that condition pretty much the same thing as this condition though? But yeah, it's gonna be slightly different, I think, because this thing might also have some velocity. Who knows? Yeah. I think this is the minimum. Minimum. length condition, you know. So you might also have maximum length condition or something like that. Anyway, the thing is, um, at that particular point, this will have some angular velocity. So yeah, and as seen as center of mass, if this has some velocity, yeah, that should obviously happen. That's gonna be very obviously happening. Here as well, as in the center of mass, this thing is going up by v naught upon 2 and this thing is going down by v naught upon 2. Most likely it's the most compressed form. We want the what do we call it? The least compressed form or the most elongated form. So if this is going velocity v and this is like also going velocity v in that case, right? Yeah. This angular momentum, okay, that's gonna be like that as well for yeah, if I view this just according to center of mass as well, it works, right? So this angular momentum, I have seen this in the ground frame, right? With respect to, I don't know, this point, which is fixed to the ground frame, okay, not to the center of mass. Yes. With respect to center of mass, what would happen is that you got v naught upon 2 in this direction and v naught upon 2 in that direction, and then it still works out to be the same thing because angular momentum of the center of mass is 0 as according to this point in the ground frame, right? Yeah, and now you got v in this direction because center of mass is inertial free and you can do conservation of angular momentum and everything. Yes, yeah. So now what do we do? You got some radius, we don't know what that radius is. Okay, what about energy conservation? That also works. Nice, energy conservation will also work. So wow, yeah, what you will have is half k times x squared. So in this case, your x is 2r minus L naught, right? This thing squared, that's is equal to half mv squared. So it's gonna be two of these guys. So whatever, half into 2m into, so finally just got v squared, and then minus you have v naught upon 2 squares, like v naught squared upon 4, right? This half can get cancelled. Yes, and that's why energy conservation and also got angular momentum conservation. So, or you know, you can just use omega and stuff to get it done. No, I'm just gonna use this thing. So this will just tell us that um, our angular momentum is gonna be like 2mv and r, of course, and that should be equal to this thing. So m L naught upon 2, and then you got v naught. Yes, so you got these two equations. Now we can figure out everything. So what was I doing? Sorry, I'm L naught over here, but and not okay. Now I'm thinking that maybe that was better, you know, omega and stuff. Nah, it's still good. We can still do it. So you got v as a function of r, isn't it? Right, just put that in there. First of all, m cancels. We want that. So v is going to be what? It's going to be L naught v naught upon 4 r. Yes, put that in there. It's going to be 2m L naught squared v naught squared upon 16 r squared minus v naught squared upon 4. So that will be like m v naught squared upon 8. Yeah, and then you just got L naught squared upon r squared, and then minus 1 upon 2, I think, right? And that's going to be equal to, so kx squared is just going to be this thing, k times, oh come on, is that real? What is this? It's so not good. It's a biquadratic without giving me what these are actually. How can I do this? If it's known to be considerably less than unity. Wait, what? Did you say that for real? It's less than, oh, wait. That's nice. If it's so maximum elongation of the spring in the process of motion, if it's known to be considerably less than unity. Wait, but what do you mean by elongation? Elongation is just is it not r? Sorry, is it not just this thing? Where it go? Where it go? Oh yeah, this thing 2r minus L naught. Is it not that? Is it something different? I don't believe that should be. Uh, what is it? Oh, wait. Why did they this 1 upon 8? Oh, it should not be that. It's gonna be like you will need 4 over here, minus 4 v naught square. But still, it's same kind of difficulty. Now, what do we do? If it's known to be considerable, let's just say your elongation is just your x value upon L naught, right? So you are saying R is approximately equal to L naught. Hey, oh, and also like it's supposed to be minus 1. That's 4 actually. Sorry, why am I missing something? Yeah, it seems I'm doing that. So once again, what was a V? It's gonna be this thing. V square V square 16 plus 1 plus V naught square upon 4. How is that V naught square upon 4? Oh yeah, V naught upon 2 squared. That makes sense. So energy conservation. Yeah. V must be like that, of course. V has to be like that. 2mvr is like that. So, oh, yeah, of course. R is actually like L naught upon 2. Close to that, I guess. So it's minus 1 upon. That's like 4, of course. Yeah, so this thing is close to 4, right? So what we can do is just say, okay, R is equal to, okay, 2R is equal to L naught plus X. So then this whole thing, what does it become? It just becomes mv naught squared upon 2, and then you can just do L naught upon 2R squared minus, well, I did take that 4 inside, so it's gonna be like 1. Now L naught upon 2R, right, that's like 2R upon L naught power negative 1. So in this case it's like power negative 2, and 2R upon L naught is just 1 plus X upon L naught, right? Yeah, and in fact what we will do is write this as 1 plus X. So here X will be the strain on the thing, right? And probably that's what they mean by elongation or something, because they are saying it's known to be considerably less than unity, right? So unity it's unitless, of course. um, so they are, I think, talking about what do we call it, uh, the strain, of course, and not the actual X value. So then our strain will call that as X right now, and we'll just set 2R to be equal to L naught into 1 plus X, and let's see what we get. So with the approximation that X is X is like very, very, very less than 1. So with that approximation, what do we get? Right, this thing just becomes mv naught squared upon 2, and then you got 1 plus X power negative 2, which is going to be 1 minus 2X, right? Well, yeah, that should be negative as well. It's not negative though. I must have messed up somewhere. Oh, it should be negative. It should be negative over here, right? So, fine. Energy conservation. Change in kinetic energy plus the change in potential energy is equal to 0. So change in potential energy is like half dx squared because it gained potential energy. And that's my negative over here. Right, now it will make sense. So this just becomes, right, it's like this thing is just 1 minus 2x. And then that minus 1, so just negative 2x. But negative of that is going to be just 2x. And then what about this other guy? So 2r minus L naught is, look at that. It's just going to be L naught times x. So there we go. Yeah, k times L naught squared, and then you got x squared, right? This should do it, in fact. Cool. So it is cancels, and then you got, yeah, that's it, huh? That's it. We got the thing. X cancels. So our x will just be mv naught squared upon k L naught squared. Yeah, mv naught squared upon k L naught. Makes sense, of course, because both are units of energy. Both have units of energy, so it will work. Or Stress is just mv not squared. Sorry, strain is mv not squared upon kl not squared. Not squared upon kl not squared. It's like approximately. Yep, this is it. So we are finally done now. Then you have this other stuff, universal gravitation. I'm not going to do all that. I think this is enough. So this is it. I will see you guys in the next video.